Welcome, everyone. The question that has puzzled humanity for centuries. How does something so heavy stay up? Let's dive into the science.
4 fundamental forces dictate flight: lift, weight, thrust, and drag. It's a delicate balance. Let's start with the hero, lift. Lift is generated by air moving over the wing. But how does this invisible medium create enough force to counter the colossal weight of a jet?
The wing's cross-sectional shape, the airfoil, is the secret. It's curved on top and flatter underneath. This shape is crucial for manipulating airflow.
Bernoulli's principle states, faster moving fluid equals lower pressure. So, the faster air on top, it is this pressure differential that generates the majority of the lift force. The high pressure from below literally pushes the wing upward against gravity.
Lift also comes from Newton's third law. The wing deflects air downwards. For every action, there is an equal and opposite reaction. The wing is pushed upwards.
So lift is a beautiful marriage of pressure dynamics and force reaction, all thanks to that simple yet brilliant airfoil shape. But lift is useless without speed. We need powerful thrust to move forward and a clever design to defeat its eternal enemy, drag. Thrust comes primarily from powerful jet engines. They suck massive amounts of air in, burn fuel, and violently push that hot air. For a plane to accelerate, thrust must be greater than drag. In steady, level flight, they are perfectly equal, creating a constant speed.
Drag comes in many forms. Parasite drag is the friction caused by the plane's shape and surface roughness, like tiny wrinkles slowing down the airflow.
Induced drag is a byproduct of generating lift itself. The pressure difference at the wingtip creates swirling vortices, which are essentially wasted energy slowing us down.
That is why modern planes have winglets. These clever additions reduce the induced drag by disrupting the vortices, making flight more efficient. Staying in the air is one thing. Staying stable and controlled is another. We rely on the control surfaces, the movers of the plane.
The elevator on the horizontal stabilizer controls pitch, meaning the nose moving up or down. Pushing it down pushes the rudder on the vertical fin controls yaw, swinging the nose left or right. It's often used with the ailerons for a coordinated turn. Ailerons on the main wings control roll. They work oppositely, one up, one down, to create differential lift, causing the plane to bank or roll sideways. Pilots combine these to perform a coordinated turn. Banking and yawing together ensures a comfortable, efficient turn. Now, for takeoff and landing, we need massive lift at low speeds. That's where high lift devices, the wing transformers, come in. Flaps extend from the back of the wing. They dramatically increase the wing's camber and area, generating huge amounts of lift for slow approach speed. Slats are on the front. They pull away to create a slot, re-energizing the airflow over the top of the wing, preventing premature separation and delaying a stall. And when we want to fall, spoilers. They deploy to intentionally destroy lift and create massive drag, helping the plane slow down and stick to the runway. On the ground, we use thrust reversers. They block the engine exhaust and redirect it forward, acting as a powerful brake, especially crucial on wet runways. We've discussed the plane's mechanisms, but flight is dependent on the very air we fly in. What happens when the air gets thinner? As we climb, air density drops dramatically. Less dense air means fewer air molecules to interact with the wing. So why fly high where there's less lift? Because low density also means much less drag. We need far less. Turbulence is just the plane flying through disorganized air. The plane is designed to withstand far greater forces than any normal atmospheric bump. Every single component is tested well beyond its expected limits. The wings, for instance, can bend and absorb stresses far. To truly understand why it stays up, we must examine the 4 forces in action through the 4 key phases of a typical flight.
Takeoff requires maximum effort. Thrust is huge to overcome drag, and with full flaps, lift is powerful enough to peel the aircraft off the ground.
In the climb, we maintain a positive rate of climb. We keep slightly more thrust and lift than needed, trading some speed for that precious altitude. Cruising altitude is the most efficient. Here, all 4 forces are perfectly balanced. The plane is neither accelerating nor climbing. To descend, pilots intentionally reduce lift and thrust. They use the flaps and slats to maintain control at those necessary low speeds near the runway. The final seconds are critical. The pilot executes the flare, trading airspeed for a soft, controlled descent until
We've covered the basics. Now, let's tackle some common myths that still float around about why planes fly.
The myth is that the top and bottom air parcels must meet at the end of the wing at the same time. They don't.
Another myth, that wings are mostly hollow. Absolutely not. They are rigid, robust structures filled with the main fuel tanks.
And finally, planes can't fly upside down. Not true for all aircraft. Aerobatic planes do it all the time.
All this physics is managed by an expert, the pilot. Their job is to constantly balance those four forces using the control surfaces.
The most crucial concept they manage is the angle of attack. A little more AOA means more lift, up to a point. Too much, and the wing stalls. Stalling means losing lift because the air separates from the wing. Pilots are trained relentlessly to reckless stall.
So the simple answer is complex. The plane doesn't fall because of the constant, dynamic, and predictable lift.
Thank you for joining me in the world of flight physics. I hope you now feel more confident soaring through the skies. Until next time, keep looking up.